Hi, I'm Emmanuel. I'm happy to see you all. I did not see you last week.
Yes.
What's your name?
Paula.
Paula. Where are you from?
Ashdod.
Ashdod. Cool. Okay, I'm Emmanuel from Petah Tikva. Joseph, Maxim, Zawon. Hi, okay. And you are? Okay. Last week we saw a mathematical introduction. I hope it was easy. It was for the transform, for the series, delta function, and stuff like that. Nothing too complicated. Today we're actually going to start learning quantum mechanics. This is my new way of teaching. I tried it in other courses. This is basically what I'm teaching from. So you could claim that it's pointless to write on the whiteboard. However, our way to learn is by actually seeing the process developing, evolving. So of course I'm going to write everything on the whiteboard. This is on a Moodle for you. If it makes it easier for you to follow me, so enjoy it. So today we will see how quantum mechanics is done. What do we actually do during this course? We will not learn why it's true. We will not learn what are the assumptions behind it. We're just going to learn the practicality. How do we do it? Okay. Let me start with a quick introduction. We had the two-slit experiment, right? And we had this thing here. Now, what was this? This was P of x, and this marker is not good. This was P of x, which is the chance of finding the particle at a specific point. We're talking about one particle, not many, one particle. It cannot split in half. It's not going to be in a few places at the same time. What is going to be in a few places in the same time is its probability density function. It's PDF, meaning there's a high chance of it being here, a lower chance of being it here, and a zero chance of being here. This is P of x. Now in quantum mechanics, we define a certain function called psi of x. This is the wave function. It acts like a wave. Did anyone here learn a course about in waves? Was this mandatory before this course?
Yes.
Okay, so yes, you all know waves. And we define P of x dx as, do we see this on the Zoom? Do you see the entire whiteboard? Yes, they do. Good. So, psi of x dx. This is a definition, so I can write it like this. And this marker is also not amazing. Did I have another one? I don't know. I had a black one. I did not. Okay. So this is the definition. This is how psi is defined. Psi is defined, so it does this. Okay, so psi can be also, P must be positive. P must be real. Psi can be negative. Psi can be complex. However, I need this to be real. This is the definition. And now I'm going to tell you what do we do with this. From this psi, I can extract all the information I know. Once I have psi, I can know the location, I can know the momentum, I can know everything to a degree. Of course, I cannot know everything because of the uncertainty principle, which is going to be one of the things we're going to learn about today. When we measure things in quantum mechanics, we use operatos. Operato is a creature you never met before. What is it? If I press control and then log out, why is it not going out? Oh, because it's this. Okay. An operator is something that acts on this wave function. You know functions, right? You've seen functions, you've seen numbers, you've seen scalars or vectors. This is something else. This thing called operator. The operator act on the wave functions. Can you see the marker at home? Hopefully you can. Okay. For example, let's look at the momentum operator. The momentum operator, it's really a bad marker. Let's go to the next one. Oh, this is better. I'm telling you that the momentum operator is P. I mark it with a hat on it. You know that something with a hat on it is a vector unit, right? X hat is one step towards x, right? Not anymore. Huh. We're going to confuse you. What?
No, it's a matrix.
It can be a matrix, but not necessarily. It can be an integral, it can be a derivative, it can be anything you want. Specifically, I can also write it as P op. Specifically, the momentum operator is going to be minus I h bar d dx. H bar is a certain constant, it's a number. It has units of h bar has units of angular momentum. I think I mentioned it last week. It's a very, very small number. Had it been 0, we would not have quantum mechanics, as we'll see in the future. So when P acts on psi, in general, when an operator f of acts on a wave function, it gives a value times the wave function. So this is an operator. It acts on a certain function, phi of x. It is going to give me a certain value. So an operator gives me a number. Is this always true? Not necessarily. It happens only when it is an eigenfunction. In general, when an operator f of acts on a wave function, here I'm going to write the word eigen. Meaning, in general, if an operator acts on something, it can change the wave function. It can do lots of things. But there's a special set of functions for each operator that if f op acts on psi, I get a certain number times the same wave function. It's not going to happen every time. Let's see when does it happen for specifically the momentum operator. Let's find such phi n of x for the momentum operator. So again, my end goal now is to find such a phi of x. So when the operator acts on phi, I get the same phi times a number. Just like in linear algebra, that you just get a number by the same thing. Okay. Now I'm remembering that P, the operator P, is this. So what I'm looking for, it's very sad, the marker that does work is not get erased. But I have tissues, let's see if it helps. Yes, it does. Maybe I should be an experimentalist instead of a theoretician. So, P operator is this. So I want to find such a function that's minus I h bar d dx acting on a certain phi of x will give me a certain number. Let's call it P over the same phi of x. This is my goal. I want to find such functions. Now, I'm telling you that in general, something that I will repeat a few times, when I act the operator P, is going to be a measurement of the momentum. If I act, the word act an operator is annoying. What does it mean? We're going to understand more as this specific lesson goes on. But when I add the operator x, I will measure the location. When I add the operator e, or h, I will measure the energy. There's different operators. So when I add the operator p on the wave function phi, it will give me the momentum times the same function. Okay, let's see what I get here. Minus I h bar d phi is equal to p phi of x dx. Okay, that's the separation of variables. D phi over phi is like I h bar p dx. No, I h bar is on the bottom. Here I'm supposed to have I h bar, right? Supposed to have minus I h bar here, right? But I multiply both sides, both the numerator and the denominator by I, so the I goes here without a minus. And what do I do now? My favorite step in math is to add snakes. The purple works. Maybe I should go on with the purple. Here I have ln of phi. Someone wants to join your meeting.
Can I?
Yeah, you can have the mouse. Enjoy it. I wonder who called it mouse. Like, it used to look like a mouse when there was a string, right?
Yes,
But
right.
not anymore. Ln of phi is equal to I p over h bar dx. Not dx, x. So phi is equal to e to the I p over h bar x. Now I can define k as p over h bar, which is again something that you might know from other courses, modern physics and stuff like that. So phi would be e to the I k x. So I'm happy. I found a function that if p acts on it, it's going to give me a certain. If the operator p acts on it, it's just going to give me the momentum. Now, something else that you did not mention, and I forgive you, is the fact that when I did the integral here, I did not add a constant of integration. So I can write here plus c, and here I can write a. Now I wish to find a, so the wave function will be normalized. Now, if you like looking at this, if there's even one person here who wants to look at it, so Maxime will have two options. Either give me the mouse, or scroll down as I teach. Is there anyone here who likes this? Yes, there is. Okay, so we got here, exactly that. We got a to the ikx. Now we want to normalize it. Oh, first we're going to show that it works. Okay, the order doesn't matter. So let's show that it works. If I have minus I h bar d dx acting on a e to the I kx, I get, well, deriving here, I get ik. So I get ik times minus I h bar times a e to the I kx. Now this is exactly fine. Here I have I times minus I is 1. K. Wait a second, I got h bar k times phi. And this is exactly the momentum. So I'm so happy because what I did when the operator acted on the wave function, I got the exact same wave function. It did not change the wave function. And I got a certain number, and that number is exactly the momentum. I could can you imagine other functions or other operators that would not save it? Like, let's imagine an operator, let's call it A, which is x, for example, or x cubed. So when A acts on phi of x, no, A is not again because it's against because we had the constant before. Let's call it operator B. Okay? When operator B acts on phi, what I have here is x cubed times e to the ikx.
For a unique solution, there will
What?
be
Now this is
one-
not a constant
Right,
and this, it's a function.
right.
It's not the same thing. So this is not an eigenfunction of this operator. This, however, is an eigenfunction of this operator. Should we normalize it? Let's normalize it. Normalizing it, I'm just going to use the delta function. I already know what the Dirac delta function is. I know that Dirac delta function is defined. Delta of x is 1 over 2 pi.
From infinity
Wait a second. The meaning
down.
here.
Yes.
The other function can be represented as integral dx e to the, what am I doing here? Integral dx e to the I kx. Right? This is the integral of,
Right.
yes, okay. I can write it even, let's do it like that. K minus k tag. Delta of k, integral dx I k minus k prime x. This here is not a function. After you integrate it, it's not a function of x anymore. It's just a function of k minus k.
Okay. Right. You
K
have
prime?
to put in the argument of the delta, right? The minus k.
K minus k prime, yes. Okay, thank you. This is one of the definitions of delta functions. We've seen a few of them last week. I don't remember if we saw this one specifically. However, this is one of the definitions, and we go from minus infinity to infinity. How do we define the normalization? What kind of normalization we want? We want not phi to be normal. We want phi
Squared.
squared to be normalized. Meaning, if I show it in the bracket notation that I presented last week, I want phi k of x, phi k prime of x to be delta of k minus k prime. K prime, is this how we'd say that in English? Because prime is derivative, no? K tag, k thing, k tilde.
No, k prime.
K prime is good? Okay, but
It has to be squared, right? The left side also.
the left side? No, this.
Oh, okay. Right.
What does this
Right.
mean? It means that I want the integral of phi k complex conjugate phi k prime dx to be delta of k minus k tag. Okay? Meaning if k and k tag, I say tag, that's how we say it in Hebrew, as you might have noticed. If k and k prime are the same, so I get phi k squared, and if they're different, they'll be 0. And this is what I get. From that I can understand that my a here is going to be 1 over 2 pi, right?
Squared.
No, 1 over
Yeah,
square root
the
of 2
square
pi. Very good. Because I need each one of them to contribute 1. So doing this, I presented to you the momentum operator class momentum operator, and we saw the eigenfunction. We saw functions that if the momentum operator acts on them, we get the same function times the momentum. Okay, now, as you might notice, we have here, where's the function? Let's talk about this. This here was phi of x, right? It's a function of x. Meaning, when I did the derivative, x was the variable and k was a certain constant, right? It came from the ph bar. It came from the fact that I wanted it to be p here. And you write here phi k. This is going to be the subscript. What does it mean? Well, you can see this e to the ikx is a function of k or a function of x. Depends how you look at it, right? So when I talk about this as an eigenfunction of the momentum operator, so far I only spoke about functions of x. Later we're going to do everything the opposite. We're going to treat x as the constant and k as the variable. We're not there yet. Variable is a mishtaneh. Okay, we're good. Okay? So k is a parameter and x is the variable. I put here the parameter. Why? Because this spans a
Vector space.
yes, it spans the space. The פורסת מרחב הילברט. It spans the Hilbert space of k, and k here is k is a continuous variable. There can be an infinite amount of k, and each one of them has its function. Okay. This was the momentum operator. Let's move to the location operator, the position operator. How did we start this momentum thing? I just told you what was the operator, and then I told you let's find a function that corresponds to this. Let's do the same here. I am telling you that the operator x, that I can also write as x up if you prefer, is x. You saw it in class already? Good. Yes. Class was today?
Yesterday.
Okay. So you saw it in class. Momentum. The position operator is simply x. Now we want to do an eigenvalue equation like that. משוואת ערכים עצמיים. An equation that just writes all the values like that. What I want is x operator times a certain function. P is we had phi before, so let's write psi now. I want it to be equal to a certain parameter, a certain value. I want the value to be exactly the location, times the same function. Here I measure the location, and this is an operator, and this is a value. Let's write it in a funnier way, okay? I want the operator acting of psi of, I can write here x minus x naught. Okay, meaning I might be in a specific location, and it's a function of x. This is, well, when I measure it, it means the function of x times psi of x minus x naught. And this would be my actual location times psi of x minus x naught. Operator, function, which is the actual operator of position, and this here is my value. It measures my value. I'm right now at x naught, and this operator is going to somehow measure my position. What is such a function? This is interesting. Multiplying this by x or multiplying it by x naught will be the same. That's funny. X is x naught, otherwise it's nothing. Do you know such a function? Does it ring a bell? Delta function! So, the answer is going to be psi of x minus x naught will be simply delta of x minus x naught. Let's show that it works, just like I did before. I started with operator. I kind of guessed. Beforehand I did it with a separation of variables. Here I just told you. This is the eigenfunction. Let's see that it works. How do I show that it works? Snakes. I add snakes here. And instead of psi, I can write here delta. Okay. Now, what is this?
XO.
What?
X. The integral.
So you know in general the way delta function works. You know that in general the integral f of x times delta of x minus x naught is dx.
Mx evaluated in x O.
Is f of x naught. So this is exactly what I have here, only that my f is simply x naught. So all this is equal to x naught. But this is equal to that. Meaning here what I can do, this here, okay, this whiteboard is going to be messy, and this is not. So you have this. So I don't feel too bad. Help my goat. This here I can definitely see this is x naught because of this. This here is equal to x naught times, x naught is a number, I can take it out of the integral, times delta of x minus x naught dx. But this is 1. So I'm going to get x naught. So I showed you that this is a good choice of an eigenfunction because I get that this equation. Multiplying, like acting the operator on psi gives me a value, the actual position times the same function. Okay. So far was so I presented you the two operators and two sets of eigenfunctions. Now we're going to move to something else called hermiticity. It's forcing me to learn English. However, my wife claims it's not English. I skipped something? Yeah. Another question we might ask is, where is the particle? At what x can it be found? The answer to this question is given by the density distribution. We see that there is no x at which the particle is preferred to be. This is a first sight at what we call the uncertainty principle. Oh, this was way before. Okay. Oh, this was way before, isn't it? Since you mentioned it, let's say beforehand we saw the eigenfunctions of the momentum operator. What I'm going to tell you now, and I will understand it more as the course goes by. When I am at an eigenstate, this is my value. Meaning, if I'm exactly at a specific location, x naught, so I am at a specific eigenfunction, delta of x minus x naught. When I'm at a specific phi k of x, which is 1 over 2 pi e to the I k x, if k is equal to 3, for example, so I'm at a very, very specific momentum. I'm at a specific function, and I have a specific momentum. If I measure my momentum, what will it be?
3.
3 what?
The momentum.
K is going to be 3. My
H bar.
Yes.
Divided H bar.
Let's see. If K is equal to 3, what is my momentum? Let's see. Minus I H bar ddx times 1 over square root of 2 pi e to the I 3x gives me minus I H bar times the i's. It gives me 3, right? 3 H bar 1 over 2 pi e to the I kx. So this here is my momentum. It's a very specific momentum. It's a number that you can know what it is. Okay? What is now my location? I am now at one specific momentum. My velocity is exactly very well defined. It is 3, positive 3, not minus 3, not 3.5, it's exactly 3. So now that I know so specifically my momentum, one might ask, what is my location? Well, my location is unknown. What is my location as a function of x? I told you before I'm very unhappy with my markers today. The p of x dx is like psi dx. So let's say this is now my psi. So my p of x is 1 over square root of 2 pi times e to the minus I kx. And now with one specific k, it's 3. Minus I 3x times 1 over 2 pi e to the plus I 3x. So now what is my location?
1 over 2 pi.
1 over square root of 2 pi. 1 over 2 pi,
Square.
sorry. So if you ask now, as a function of x, where will I be? Well, I'm going to be here. This is the height of my function. And my chances of being here are this. P of x dx, so my chances of being here, my chances of being here are the same. Meaning I am everywhere. If you know exactly my momentum, then your knowledge of my position is an absolute 0. Wait, what does it mean? What? Yes, that's what we get here. All I told you today, again, I'm not telling you what are the assumptions and how did those smart people figure it out. That's just what we see in reality. When you know the exact momentum, you know nothing about the location. Okay. Now we're going to talk about hermeticity. Okay, there was a guy called Hermit. How do you open a new one? Yeah, whatever. Hermit. He was a good guy, probably French, right? Hermit. Okay. Yeah, here. Hermit also known. Okay, not this guy. For other. Okay, not worth it.
The one of the polynomials of Fermi.
Yeah, this guy. So we're going to see Hermit's polynomial later in this course, hopefully, when we get to talking about quantum. Why do you know this? Did you take this course in the past or something? Kind of. Okay. So operators can be Hermitian or not Hermitian. What does it mean that they're Hermitian? There's a few ways. It has to do also, I think in linear algebra you saw that a matrix can be Hermitian or not. There's a few ways of representing what does it mean that an operator is Hermitian, and I'm going to talk about functions. I'm going to give you one definition of what is an Hermitian operator. What is the definition? That if I do the integral, I define it for integral? Yes, I do. If I do the integral of psi 1 f operator psi 2 dx, it is equal to doing the integral of f operator prime psi 1 a complex aggregate times psi 2 dx. And in order for it to be a little clearer, I'm going to use brackets. Here, I first act the operator f on the function psi 2. Then I multiply by this, and only then I integrate. Here, instead of f operator acting on psi 2, it acts on psi 1. If you're talking about derivatives, so here there's a derivative of this, and here there's a derivative of that, for example, of that. However, when I move it to the left, I also take the complex conjugate of it. If this is true, and it's not always true, so So I define this operator as Hermitian operator. Let's take an example. Let's talk, for example, I don't know, about the momentum operator. That's a good idea. Let's show it for the momentum operator. So I'm reminding you that P is minus I h bar ddx, and now I'm going to see why this I is necessary. If I do psi 1 prime, now let's act. I'm going to start with the left-hand side. Left-hand side, I get the integral of psi 1 prime, not prime, complex conjugate, times minus I h bar psi 2 prime.
We're missing the partial derivative.
No, that's why I did prime.
Ah.
Aha. Is this clear enough?
Yes.
This is the partial derivative with respect to x. We have no other derivatives here. Okay, however, when I take this side, what I get here will be left side. Left side. Right side. And I'll take the integral of. Now I want to take the complex conjugate of it. So I have I h bar of ddx times psi 1 complex conjugate. And only then I'm going to multiply by psi 2 and take the integral dx. How do I show this is equal to that? Do you know any mathematical way or trick or tool that you can use in order to move the derivative from one component to the other? What? I was thinking more about the integration by parts. Same thing. Did you mean that?
Yeah, it follows from it.
Sababa. What's your name?
Eliyahu.
Eliyahu. I have a feeling you're from Israel. Are you from Israel?
Of course.
So, as you know, the integral of, well, u prime v is going to be uv minus the integral of uv prime. Yay, we like this, because this we understand. Let's add numbers, minus infinity to infinity, and from here, I also put the limits, right? This is going to be important. The trick that I'm going to do now, we're going to do a few times throughout this course. What do I do now? I want to move the derivative from here to here. So I take this as, and this as v prime, and this as u. So I get, well, the I h bar I can take out. Now I have psi 1 complex psi 2 from minus infinity to infinity.
That is 0, right?
Wait, don't ruin it.
We said yesterday.
Wait. And then, minus, because of this minus, the integral from minus infinity to infinity of, I move the derivative to here. So, psi 1 complex conjugate, psi 2 dx. Joseph, do you see what this is?
0.
Why?
Because we have to be the wave function to be normalized.
Yes. That's how we are physicists. If we're not normal, we want this our function to be. So the only way that a function can be normalized is if at the end it's 0. That's one of the definitions of Hitkantut. Yes, thank you. Right? If something at the infinity is not 0, it's not going to converge.
Shouldn't there be a derivative inside of the integral?
What, here? Yes. So this is 0. And then I'm left with this, which is exactly that. So I'm all happy. Now I was wondering, did you ever see a wave function that is not normalized? Did you ever see a wave function that in infinity is not 0? I'll give you a hint.
The delta function can be infinity.
Yes, no, but it is normalized. The area under it is 1.
Right.
The uniform distribution that you showed earlier.
Yes, I just saw the uniform difference distribution of 1 over 2 pi from minus infinity to infinity. This was normalized. Right? From this we'll see next week that indeed you cannot have a particle with one specific momentum. Because if you have a free particle, if you have it in a box, so you're good, because you can say it's definitely in the box, and then you can normalize the wave function. But if it's not in the box, if it's actually from minus infinity to infinity, it cannot have one specific momentum, because then my position is all over the place and it cannot be normalized. Was this clear? Yes, okay. So throughout this course, we're going to see lots of operators. We're going to have fun with them. We're going to become friendly with them. Not all of them are going to be Hermitian. But everything that measures some physical size must be Hermitian. Can you give me an example for something physical that one can measure?
Angular momentum.
Angular momentum, yes. So we are going to have an angular momentum operator. And the angular momentum operator is going to be Hermitian, which means I can choose always to act it well either in this or in that, but complex conjugates. Can you give me, now someone else, give me an example of something physical that I might want to measure in the world? Energy, yes. If I want to measure the energy, it is going to be a Hermitian operator. Can you give me of something that's not Hermitian operator?
Time evolution.
What?
Time evolution.
So the time evolution I always get confused with, but the easiest thing would be I can make up an operator which will be
A derivative.
minus h bar ddx. Right? I saw already that if I need the I in the momentum operator. You didn't have the I, so it wouldn't work. However, we are going to see throughout this course operators that are not Hermitian but are necessary. But we're not there yet. Okay. Now let's see some operators. The operator of position is x operator is going to be simply multiplying by x. The momentum, we already saw that P is minus I h bar ddx. And energy is going to be, well, E up. Because we're usually going to mark it with H. There's a few ways of saying it, but here we're just going to call it IH bar ddt. There can be kinetic energy. And kinetic energy, in general I know that it's half mv squared, right? Not anymore. From now on it's going to be p squared over 2m.
Hamilton's version, right?
What?
Hamilton's version.
Make you say so?
From the Hamiltonian.
I know of that, but I'm kind of consciously trying to like push it to my subconscious. I don't like like analytical mechanics.
Okay.
So yes, it has to do with Hamilton formulation of Lagrangian and all that. Suppress. Yeah, not suppress it. But you know, if you know that P is equal to mv, so P squared is m squared v squared, and you get from here to here. Therefore, it is going to be P squared divided by 2m. 2m is still going to be a number. P, however, is going to be that. So if I take the square root of that, what do I get? Minus h bar minus h bar squared d dx squared
Over 2n.
over 2n. Okay, here in the numerator I have p squared. When I take the square of minus I squared, I get I squared is minus 1, minus 1. Ah, so give me minus 1 feet. That's good. So I get here the minus h bar squared is h bar squared. I square the derivative, which means I take the second derivative. I divide by 2m. So acting this operator on a wave function will measure the kinetic energy. Okay, these are some of the operators that we're going to see throughout this semester. Representations. I wanted to say something now. I don't remember what. Okay, I still hold that it's very unpleasant, not very, a little unpleasant to hear the same person speaking for an hour and a half. So I need something to break my monotonous voice. So, what did your name is? Paula is going to tell us about herself. Yes, you have 30 seconds. There's more. How about your second name by none? Okay, so say it in Hebrew and I'll translate. Okay, what did you do before going to Bar Ilan?
Come to a walk here.
No, in general, like a year ago. More than a year and a half ago?
הייתי בכיתה י'.
Oh, you're in high school. Okay. I was in high school. A year and a half before coming here, she was in 10th grade. Do you have any friends from Rehovot also learning here with you?
Yes.
Okay. Okay, so far everything that you've seen today with me, we spoke about stuff as a function of x. X was the variable, and sometimes when we had momentum, we spoke about momentum as a certain constant. I have a specific, I can have one or others, I can have different momentums. Oh yeah, I know what I wanted to say. I told you before that my momentum is h bar k, right? I just want to talk about units. I told you that h bar has units of angular momentum. What is angular momentum? When I go back to mechanics, so it is MRV, right? Stuff like that. I never remember units of stuff. I need to go back to the basics every time. So I have kilogram times meter squared over second. Okay, what do I have here? In fact, K is units of 1 over meter, which is why h bar is kilogram meters over second, which is like kilogram times velocity, which is momentum, which is like mv, right? This is good.
Wait,
I love units.
shouldn't really be that because the units of P and the units of H bar are not the same. So
Exactly, because K fixes the unit, because K is 1 over meter.
no, but you watch H has units of momentum.
Oh. You happy now? Guys, Eliyahu is happy. Does it make us all happy? Good. Thank you. So everything that I spoke about today had, I spoke as x as the variable and K was sometimes a constant. Now we're going to do the exact opposite. Why? Because sometimes it's very convenient to talk about everything in the momentum phase. In the momentum space. It's, in my eyes, each one with their difficulties, this is for me the most confusing part of the course. What I'm going to show now. You saw in the course of waves, possibly, how you can see everything in the time dimension, in the time space, or in the frequency space. It's exactly the same, only now instead of talking about frequency in time, we're talking about frequency in space, 1 over x. So let's talk about it. Okay, in the position space, what I wanted it in the position space, t of xt dx, there's no dx here for some reason, but it's a mistake. The chances of finding a particle in a specific location x at times t times dx, the width of my measuring tool, was psi of xt squared. When I do this, of course, I mean complex conjugate times the not complex conjugate dx. Here, there's no k. Well, psi itself might have a specific k, but k is a number. Now, I want to find a certain in the momentum space. I want a certain p of kt dk to be a certain psi of k t dk, and my way of usually showing it is by putting a tilde here. Because it reminds me that this is in the space dimension, and this is in a space, and this is the position space, and this is in the momentum space, and this would be simply the Fourier transform. They'll be the Fourier transform of each other, just like you saw in other courses before. Have you all seen such things? Okay. Now, psi, let's write it down. Psi tilde of k t would be, I still don't know how to write this fancy f. Can anyone help me?
Yeah.
You have to do like.
You do like an integral and then a horizontal line, and then the middle line.
Like this?
That's how I.
Yeah?
I do it first a line like this, and then no, in horizontal and with a hat.
Okay, we'll have a drawing class after.
The beauty is to see an integral in everything.
It's fascinating how your definition of beauty has changed throughout the years. You're here and you lost all sense of art. F of psi of x t, and as you know, if you Fourier transform something wide is narrow, if Fourier transform something narrow is wide, which means again uncertainty principle. Meaning if I have a very narrow function of x, I know exactly or quite specifically what is my position. So my Fourier transform will be very wide as a function of k. I'm in many different values of k. I have no idea what is my momentum. Okay. I can write here 1 over square root of 2 pi integral psi of x e to the minus I kx dx.
Oh, and just a comment, the Fourier transform above should be squared.
What?
In the second line.
Here?
Yeah.
Oh yes, you're right. Thank you. Hello. You look familiar. Did I ever teach you?
Yes, of course, on Netflix.
What's your name?
I'm Ben.
Again? Ben.
Ben.
On. Okay. Now I'm going to find everything that I spoke about so far, the operators and the eigenfunctions of x and p, all of them were in the position space. I can also describe all of them in the momentum space. It is super confusing. I can ask you what is the momentum when your function is the location space and when your function is in the momentum space. I can ask you what is, it's very, very confusing. So, one of the reasons I asked you to teach this course a few years ago, because when I did it at second year, I really liked it, I really enjoyed it, but I didn't understand it. I mean, I enjoyed it, it was fun, but I didn't feel like I fully understood it. And in my eyes, the best way of understanding something is teaching it, at least for me. So I taught it, and now I understand it better, which is fun. My students in the first year were the victims of my desire. So we already know what is the momentum, what are the eigen functions of the momentum in the position space. Eigen functions of the momentum in the position space are what we saw before. Phi k of x was 1 over square root of 2 pi e to the I kx. If I want to know what is, meaning if I have one specific momentum, this is the way to describe it, right? That's how we saw it. One specific momentum k, this is the way to describe it. How, if this is indeed my momentum, how would you represent it in the momentum space? Well, I would do the Fourier transform. So I do an integral, and then I do this, and this, and this, and this. This is my Fourier transform of phi k of x, which is integral from minus infinity to infinity. I have 1 over square root of 2 pi coming from here, and another one from the Fourier transform. Altogether 1 over 2 pi e to the I kx coming from here, e to the minus I kx coming from here, integral dx. Hey, I know this guy. This is a delta function. This is delta of k minus k prime, right? So k prime, let's have here a k prime. K prime is my specific, wait a second. Here. K prime, let's say, is my specific momentum. I have one specific momentum, so my way of describing it in the position space is this one, right? If I want to do the Fourier transform of it, it is this. K prime is like my number, and k here is going to be my Fourier transform parameter, the momentum. I get here this, which means if k and k prime are the same, so I have, so this is my momentum, and otherwise I have a 0. All this leads to me understanding, well, the other side would be asking what is the eigenfunction of the position in the momentum space. How confusing is that? Well, we saw before that the eigenfunction of the position in the position space are delta function, right? Delta of x minus x naught. So if I translate it to the momentum space, I already saw that the Fourier transform of the exponent is a delta, so the Fourier transform of a delta is a exponent. Which is why I have here a beautiful, beautiful, beautiful chart. I'm trying to sum up the operators and the function in different representation. Can you please share screen? I could write it all down, but it would be a shame.
Right.
Yes, present now. Is it a present? No. Entire screen is the easiest to do. Okay, amazing. So what do we have here? Let's start with the position space. The position space. Okay, so the position space here, we see here the action. The action is what is actually the operator. We saw that if I want to measure the location, all I need to do is multiply by x. However, if I want to measure the momentum, I need to multiply by minus IH bar and do a derivative with respect to x. The functions, well, if I have a specific rotation, it is delta. If I have a specific momentum, it is e to the I k naught x over square root of 2 pi. And k naught was my specific momentum. X naught was my specific location. X and K were the, and here I have, these two things are a function of X, you see that. If I do all this in the momentum space, so I also need to define the operators. Meaning, I just did the Fourier transform of delta here, was this exponent here, and the Fourier transform of the exponent here was this delta. But then again, I can ask, what is the operator? The only thing that I gave you, that you had as a given in this class, was these two operators. The operators x, well, I want to be in the recording and also here. The thing that I just gave you this course today as an assumption was this and this, these two operators. And from this, I found the eigenfunctions. I looked for functions that if I act the operator on them, all I get is the number, the value. And then I did the Fourier transform in order to get the eigenfunctions in the momentum space, which here is the exponent and here is the delta. What I did not do, I'm just telling you, again, but it's quite easy to show, is what are the operators in the momentum space. Do you know any operator that if you act it on delta, all you get is a number? Yeah, we saw it half an hour ago. It is just multiplying by the variable. The variable here is p. Do you know any function that acting it on the exponent is going to do a good measurement and give you just a number? Yes, e minus IH bar ddp. So this is an important chart. Okay? Okay. All this was an introduction. What do I mean it was an introduction? This was not a specific problem that I asked you to show. There's a given psi. Tell me what is the location. I just showed you the formulas. These are the formulas. All I did today was just showing you why this is true and how it works. I also defined what is a Hermitian operator. Now, we're going to actually use it. And the most classical questions in this course are, you're given a certain wave function, tell me everything. When I say classical, I don't mean classical as opposed to quantum. It's one of my plans for this course. You'll have to live with it. We're going to hear it many times. Classical, quantum, okay. So you're given a certain wave function. Find the mean position, find the mean momentum, find the mean position squared, the mean energy, kinetic energy, etc., etc. And what I did not do yet is telling you how this definition here. Definition: mean. The mean of height. 1, 2, 3, 4, 5, 6, 7. We have 10 people in this room. Okay. The mean height is, well, you take each height times the chances of finding someone with this height in this class, right? So also here, the mean position would be, if you wish, you could do this in an integral in terms of summation. You want to take all of the positions times the chance of finding someone in that position, right? Integral dx. This is the definition of the mean. Let's do it in our quantum mechanic language. Instead of p, we're going to write psi complex conjugate psi. However, we like sandwiches. So the way we're going to show it is the mean of a certain observable, f, would be psi f psi. This is again the Barty notation. This means it can be these two can be vector, row and column, or it can be a function. And this one here is the complex conjugate. What it means here in the language of functions, which is what we're going to see in the next few weeks, we're going to have psi complex conjugate times the operator acting here, or you can act the complex conjugate on this, as long as we're talking about a Hermitian operator. Integrate dx, and here you get the mean of f. What is f? It can be anything I want. It can be momentum, it can be momentum squared. Momentum squared is very related to kinetic energy. I can ask you also what is the momentum cubed. I can ask you that. I don't know what's the meaning of that, but okay. This is super important. This is the kind of question that you're going to have all the time throughout this course. What does it mean position? What does it mean momentum, etc., etc. And this is always going to be the way to do it. Now, sometimes the operator can be a derivative or a multiplication or stuff like that. These two can be as disgusting as you want. Meaning, if you have a delta or one exponent, then it's easy. But if you have a superposition of a few deltas, if you have exponent, or if you have a square or triangle or anything else, so you're going to have to break it down to eigenfunctions, which is why we did a Fourier transform. Remember? Last week we did a Fourier series. So we had like a absolute value, and we said, okay, I'm many sines and cosines. If you act on sine and cosine, it's easier than acting on a triangle. Okay, you're going to have a certain particle, a e to the minus alpha x, absolute value of x. First I want to understand a little bit what it looks like. This is psi, the function of x, and I understand that it is going to look kind of, well, when x is positive, e to the 0 is 1, and goes here exponentially, right? It is also symmetric, it is an even function, so it's going to be like this. This is psi of x. Okay, good. Now, we're told psi is equal to a e to the minus alpha x. We are asked to see, find a. This is going to be through normalization. We want every wave function to be normalized. And then they want us to find x squared p and e squared. Fun. Looks fun? It won't be as bad as you think. Why? Because we can copy it. First of all, finding a is going to be a simple normalization. We write 1 is equal to the integral of psi complex conjugate psi dx. Taking the complex conjugate means nothing because there is no I here. I get a squared times e to the minus 2 alpha x with a snake here. Dx from minus infinity to infinity must equal to 1. The integral of a... Hey, wait a second. This is an even function. So I take here from 0 to infinity and multiply by 2. And this is 2a squared divided by minus 2 alpha from 0 to infinity. I get a plus.
It should be plus 2 alpha.
What?
It should be plus 2 alpha because the function is positive.
Be plus 2 alpha because the function is positive. What?
Yeah, e to the minus 2 alpha x is a positive number, so the integral cannot be negative. It has to be plus 2 alpha.
No, what I have here is 0 from here. The lower limit of the integral is going to give me a squared over alpha, no?
Oh yeah, okay.
Okay? And this must be equal to 1, which is why a is going to be 1 over, a is going to be square root of alpha, right? Is this what I have here? Where a and alpha are constant, find average. Okay, I wasn't asked to find a. What a waste of time. Okay, since I found a already, I'm going to tell you something about it. Did you see somewhere that I kind of lied here?
A can be a complex number.
Yes, a can be a complex number. A here can be complex number, so here it's not just A squared, it's A absolute value squared, right? And it stays here. A can be square root of alpha. Also, A could also be square root of alpha times e to the I phi. It can be anything outside square root of alpha, but it can be also, it can have a phase. This thing is called a global phase, and it is not important. We do not consider it in this course, or any course, because there's no way of measuring it. I'll mention it when it's going to show up again. Sometimes I can have a phase between two states, and then it's important. Here, when I have just one wave function, so the phase of it is not important. If my wave function would have been I don't know, AE to the I minus I alpha, no I. Let's say this would have been my wave function. So the phase between A and B would be important. I would mark A is equal to square root of alpha, or maybe I would have another 2 here, and B would be square root of 2 alpha times e to the I phi, when I have a phase between two different states. When I have just one, so the phase is not interesting, it's called a global phase, and I'm not expecting you to fully understand what I just said. When it's going to come up again, then you'll understand it better. So this is my function. Now I need to find these things. I'm going to erase everything that's not blue on the whiteboard. Okay, what is x? This is going to be easy. X, this is how I say the mean position. Okay? I'm not going to write x like this because it's too confusing. Because we have x operator, we have, this is the way we write the mean of x. And it is going to be, a e to the minus alpha x times x times ae to minus alpha x. I can write it as an integral of a squared e to the minus 2 alpha x times x dx. Even function times odd function, symmetric limits, 0, which makes sense. What is my mean position? I can see with my own eyes that it is 0. Okay. Now, what would happen if I ask what is the mean position squared? Well, since I want to save ink and time, I'm just going to do this. Okay? What are going to be my limits? It is an even function, so they're going to be from 0 to infinity times 2. How do I do this?
Integration by parts.
Integration by part twice?
We can do with a table.
Oh yeah, I heard about that. Student showed it to me. I was in shock because I always take all the time nuggets. Okay. How does it work? You write u and v. E to the minus 2 alpha. I never did this with a table. AE to the minus alpha x. AE to the minus alpha x over minus alpha. Is this how you do it?
Oh, I do it in another way, but it's the same concept.
I never did it. It's the first time in my life that I'm doing it. I'm very
yes, like that. So x squared, now 2x, now x, now 2, no.
Oh, I forgot it is. Okay, like this?
There's a 2 in the second. You need to derivate 2x, and it's
oh, here.
2.
Yeah, I have to.
in the upper one.
What?
Right. And now you have to go to 0.
Okay. So here I have 0, and you have a e to the minus alpha x times minus alpha cubed.
Right. And you have to multiply, but in the first row is a plus
So-
sign.
So
You
the
have to
first,
in
I already see. Okay, the first is gonna be this. Okay, this is gonna be with a plus. This is gonna be with a minus.
No, in diagonal.
It's
In diagonal.
diagonal.
So this times this
Yes,
with a plus,
with a plus,
and this times this with a minus,
with a minus, right?
and this
With
times
a
with a plus, and that's it.
That's it. And you just
Okay. Okay, so this is the plus. Now, of course, who wins? This or the exponent?
exponent.
Exponent wins, and this goes to 0, so it gives me 0. Okay, this times this, who wins?
Exponent.
Exponent, so it gives me 0. So I'm left with this times this. I don't have to integrate on it, right? It's just this.
Right. And now, but in the last one, the 0 value counts.
Why, you do this times this?
No, no, yeah, like that.
No, now my integral is 2a squared. Oh, you mean I need to put in the limits? Yes. And you have now this with the lower limit of 0. So this gives me another minus. So I have times 2a. Oh, I can ignore that a. All this was without the a. The a is not part of the a squared. I'm ignoring the a. Okay, 2a squared times 2 over alpha cubed. Okay, is this what we have here? Go down, please. A squared over 2 alpha cubed. Okay, not bad, not bad. Right? We missed a 2 somewhere. Or they did. Whatever. We get. Did I miss a 2?
Ah, in the exponent, there's a 2. So
Oh, here.
every time we need to go
Every time there's alpha, there's 2 alpha actually.
right.
So now it's like this.
Right.
Okay. So this is a squared over
2 alpha.
2 alpha cubed. Is this the answer? Yes. Good. This is my. Are we still sharing screen?
Yes. Stop.
I think so. Yes. Can you see if they asked if they wrote anything? 10 minutes to the end of the lesson. In the meet, did they ask anything on the chat?
No.
No? Okay. Maxime, thank you very much. You're amazing. It was a pun because Maxime in Hebrew means amazing. I'm not the first one to do this, am I?
No.
What?
What's the first one?
Yeah, but it's a positive pun.
Yeah.
Very positive. I even mean it. Okay, now I want to measure P and P squared. How do I do that? Exactly the same way. P would be in the integral from minus infinity to infinity e to the minus 2 alpha x. Again, taking the complex conjugate does not matter. And wait a second, I cannot do that. Why can't I do that? Because I need to take the derivative of the second one. I'm going to do here minus alpha x. Oh, come on! So close. Sorry, did it hit you?
No.
It touched the garbage. Okay, now I need to do minus I h bar. When I do the derivative of the second one, I have
An alpha.
an alpha or minus alpha? It depends, right? Oh, this is annoying. I need to
In 2 cases.
take both cases.
You can't.
What I could do is move to the momentum phase or something. Let's see what they did here.
As a move to another phase.
Yeah, they're doing the Fourier transform. Okay. I guess we're gonna do this. Let's find, I could do this and do better.
Can't you say something about the parity of the Fourier transform if you know that the function itself is even? Like, if the function is even.
Yes, I don't remember. I think if it's even here, so also it's going to be even in the Fourier. Well, I can guess already because it's symmetric. That's going to be the mean momentum is going to be 0. There's nothing uneven about this function. So my guess would be that P is that this is 0. Okay, what I could do is do here e to the minus alpha x prime dx, divide it to different areas, to the positive x and the negative x, do the derivative, and then add them. The other option is to move it to the momentum space. I do not have much time. Let's move it to the momentum space. I do the Fourier transform of a e to the minus alpha x. And since you already know how to do a Fourier transform, I'm just going to copy here. And it comes out to be, you can see it in the lecture notes, a times 2 alpha over square root of 2 pi alpha squared plus k squared. This is the wave function. So now if I do the integral of this times, what is the momentum operator now? It's not going to be the derivative, it's going to be p because we just moved to the momentum space. If I move now to the momentum space and I do a 2 alpha over root of 2 pi alpha squared plus k squared times, all this is squared now because we're doing psi squared times p. What is p? P is h bar k, right? This would be now my mean momentum, right? Hey, it is 0 again. This is an even function of k, and this is an odd function. I multiply them, I get an odd function, integral from minus infinity to infinity, and I get a 0. All I skipped here, I know it's unpleasant. Even when you do a certain addition, if you don't fully see it yourself, it doesn't feel as funny it feels funny in your tummy. I know. It's annoying that I skipped this. I apologize. You can see it here. But once you see that this is the Fourier transform, I can very easily see that my mean momentum is going to be 0. So my mean momentum is 0. My mean position is 0. The mean of my position squared is this. What is going to be the mean of my momentum squared? It is going to be this. It will be the same thing that I did before, only now I'm going to put a square here and a square here. What I have now is, again, an unpleasant integral, right? Because I need to put it from 0 to, I'm going to take the even part from 0, it's an even function, I'm going to take it from 0 to infinity. As you see, there's tricks of even and uneven, and tricks of Fourier transform, and tricks of integration by parts. I'm going to come up many times in this course. I do this integral, and you know, to solve this, you need to know complex analysis, which you will learn in Maths 4. Okay, you don't know how to do this, and I also don't. I forgot. I actually got a good grade on this course, I think. Much better than quantum mechanics. You get a certain number. What you get here is that p squared is, I'm going to write it down. I think next time they're going to bring me a new marker, a new eraser. I get here that it is equal to h bar squared a squared alpha. And from here we get to the uncertainty principle. all I told you until now, I mentioned the uncertainty principle like at least like 5 times, but all I told you was a qualitative understanding. I know a lot about my space, about my position, I know nothing about my momentum, and vice versa. This is wide, this is narrow. Okay, let's see the definition. The definition of the uncertainty principle is as follows. First, I need to define delta x. Delta x is the square root of x squared minus x squared. I already know both of these, right? That's simply that. So we take the, okay, good. Delta p is the square root of, same thing, p squared minus p squared. It's the STD, if you wish. This times this is going to be always more than h bar over 2. Delta x, delta p is going to be more or equal to h bar over 2. Had it been 0, quantum mechanics would not exist. Let's see it here. What is this times this? Sorry, I need to take the square root of it. I do this minus 0 and then take the square root. I get the delta x, delta p here is a over square root of 2 alpha cubed times h bar a square root of alpha. Okay, this is h bar times a squared. What is a squared? I think we saw that a squared is alpha.
Yeah, it's alpha.
A squared.
It was the root square of alpha. Right?
Okay, so a squared is alpha. If a squared is alpha, so I get h bar over square root of 2. Now, might be confusing, but h bar over square root of 2 is bigger than h bar over 2. Since a squared is alpha, so all of these 1, 2, this is 1 alpha. Am I right here?
Yeah.
Yes, okay. So all I'm left here is this. So this is the uncertainty principle. My time is up. Let's go down for a little bit. Let's see what I missed. Oh, there's another example here. No, this is what we saw. Is there anything else? Ah, we did everything. Okay, the one thing I did not do, and might appear in the homework, is time evolution. Did you see time evolution in the lecture? Okay, so everything that has to do with time evolution in the homework, don't do. I'm going to write it down here. How was it, man? Thank you for listening.